Hello, I will talk about our paper with Petr Savický, Inhomogeneous random two-set, and the companion paper about digraphons. And I'm now trying to post videos of my research, compensate for my unwillingness to travel much due to environmental reasons. So here is what the talk would be in 1 minute. There is this model of random k-sat, where it's this very much studied model of random Boolean formulae. Now, the first non-trivial k is k equals 2, but still this k equals 2 is much, much easier than k at least 3. In particular, this k equals 2 was solved, threshold for asymptotic almost sure satisfiability versus unsatisfiability was solved in the 80s using more or less graph theoretic methods. What we do in this paper, we introduce an inhomogeneous version of random two-set, very much like Bolobash-Jansson-Riordan, generalize the model of Erdős-Rényi random graphs to the inhomogeneous setting. Now, importantly, the underlying graph theoretic structure is not random inhomogeneous graphs, but random inhomogeneous digraphs. And what this leads to is analysis of inhomogeneous random digraphs, which is involved from a functional theoretic perspective. In particular, it leads to analysis of operators which are non-self-adjoint, so their spectral properties are much more difficult. So I will try to cover all these aspects. And here is the overview of the talk. It will have 3 parts. In the first part, I will try to give some sort of graph theoretic preparation. So I will talk about inhomogeneous random graphs. I will talk about spectral properties of graphons. So these are things which have been well known, well studied for 2 decades at least. But then as part of these preparations, I will also talk about spectral properties of digraphons, which is what is done in this companion paper we have with Petr. And then I will recall what this random k-set model and state our main theorem about the inhomogeneous version. And I will try to indicate some parts of the proof as well. There will be quite a lot from both of the papers that appeared on the first slide. Okay, so let's dive into the first part. So I will quickly recall what the Erdős-Rényi random graph is, because I need to have an example theorem that I will use to demonstrate the extra powers of the Bolobash-Jansson-Riordan model. Okay, so what you have a fixed integer, and that's the number of vertices, and you have a parameter p, which is a number between 0 and 1, and that's probability of insertion of any given pair of vertices as an edge of your random graph. And somehow turns out that most of the time you are looking at the asymptotics as n goes to infinity, and most of the time p changes as n goes to infinity. So it's a function of n, and it's a function of n which tends to 0. And there are various regimes which are interesting. For example, if you want to study connectivity, you are looking at the scale log n over n. But what we will be looking at throughout the whole talk will be the sparsest meaningful regime, where p is constant over n. Okay, so we are looking at g n comma c over n, where c is a constant. So arguably the most important regime, the most important theorem in the theory of random graphs is this phase transition of the giant component, which was observed already by Erdős and Rényi at the very beginnings of the theory. So in particular, they proved that when your constant is less than 1, then all the components of this random graph are typically extremely small, say at most logarithmic. Whereas, so something very dramatic happens at c equals 1, when when the constant gets bigger than 1, then there is the so-called giant component. That's a single component whose order is linear. Okay, and so the constant, so how big exactly it is, here it's the leading constant is denoted by S. It of course depends on C. Okay, so now let's remember that theorem, and now I want to introduce a far-reaching generalization following monumental work of Bolobash, Jansson, and Riordan, and there is subsequent work of Bolobash, Box-Chase, Jansson, and Riordan. So I will not be distinguishing that much between these two papers. And this is a project which reflects developments in graph limit theory by Lovász, Szegedy, Borgs, Chase, Sors, and Veszder-Gombi. So these are, in some sense, parallel developments, but this inhomogeneous random graph one is clearly inspired by what was happening in the graph limit project. And what happens here is you change the parameterization of the model, and instead of having a single constant C, a real number, you introduce a much more complicated parameterization, which is by something I would call a symmetric kernel. And what a symmetric kernel is, it's a function on the unit square, which is Lebesgue measurable, and it's symmetric, meaning wxy is equal to wyx for every x and y. And here on this picture, I am taking the codomain of that function to be 0 to 999. That, of course, that range is not important. The definition I will be working with is that it's a general L-infinity functions, a symmetric one. For a lot of things, including our results with Petr, you could generalize this to L1 functions, or at least parts of the results. The analytic subtlety, I will not distinguish between them that much in this talk. But what is definitely important is that the function is non-negative. And once you have such a function, then you can use different shades of gray to depict it on a picture, like I'm doing here. Okay? And note also that I'm using what you might find as a non-standard orientation of the Euclidean plane. Well, it's not so non-standard. This is the orientation you are used to in matrix theory, right? Where the main diagonal runs in a direction which is perpendicular to the direction in which it runs in the standard orientation of the Euclidean plane. Well, this is because there are good reasons to think of W as some sort of infinitesimal version of a matrix, which somehow got squeezed into the unit square. So it's a symmetric non-negative matrix, some measurable version of it. Okay, so now we have a graph on W, and we need to define this inhomogeneous random graph, Gn, W over n. So there is no randomness in the vertex set. The vertex set are just vertices 1 up to n. And now there are two steps of randomness. The first is that for each vertex, you generate its representative using the Lebesgue measure on the unit interval. So you generate its representative in the unit interval. Okay, so you have generated these n many points, and then you can reflect them. So they live both in the column space and the row space of your graphon, of your matrix. Okay, and now you need to decide which pairs of vertices will form edges and which will form non-edges. So, okay, so on this picture, I'm doing this decision for the pair 1, 4. One form an edge with probability. So now you look in the graphon at position given y x1 and x4. Alternatively, you might look at position given by x4 and x1. So somehow to capture the symmetric nature of a non-oriented graph, you can use either the values are the same because the graphon was a symmetric function. And you use that number divided by n as the probability of inserting that edge. Okay, and you do that for every pair of vertices. Okay, remember, I'm using as a in this running example, W has values upper bounded by 999. So when I say make this an edge with probability w xy comma xj over n, strictly speaking, I need for this to make sense n to be at least 999. Otherwise, I would have probability bigger than 1. Okay, so strictly speaking, I would take minimum of that value with 1 as the edge insertion probability, and then the formula would make sense even for n's which are smaller than 999, and actually it would make sense even, say, for functions which are L1 but unbounded. Okay, so that's the definition of the model. The main motivation behind it is that it brings some inhomogeneity into your world, right? You, for example, might want to model friendships on the planet. Now, of course, these friendships do not, even if you assume that they are generated at random, then obviously, say, two people living geographically close to each other have a completely different probability of creating a friendship between them than two people living on the opposite parts of the planet. So now I just recall this giant component theorem. The largest component in Gn C over n. So I'm back to the ordinary homogeneous R-Renyi random graph. The largest component is either very small or very large, depending on this very simple condition: C is less than 1 or C is bigger than 1. Okay, and now we may ask ourselves, okay, so what about these inhomogeneous random graphs, where obviously in my kernel, in my graphon, I have some parts which may take small values, say smaller than 1. I may have some parts which have larger values than 1. So is there such a condition here? And indeed, such a condition does exist, and it's formulated in terms of the spectral radius. And I will have a slide on what the spectral radius of a graphon is. But you recover, so this is a generalization of the theorem of R-Renyi. Why? Because the ordinary R-Renyi graph, Gn, C over n, corresponds to this Bolobash-Janson-Riordan model when W is the constant C function, and the spectral radius of the constant C function happens to be C. Okay, this is more general than the R-Renyi theorem. And let me just say, the Bolobash-Janson-Riordan in fact introduced a slightly more general model than what I'm talking about, but the price they have to pay for this extra generality is that they can only work with graphons which are continuous on the unit square. Okay, now you could obtain this theorem even for discontinuous graphons by the subsequent work by Bolobash, Box-Chess, and Riordan. Somehow I want to emphasize it already here. What we do with Petr is for potentially discontinuous kernels, and the price we had to pay for being able to deal with discontinuous kernels was quite a bit of what I found non-trivial functional analysis. So now we want to see what the spectral radius is, or more generally, I want to explain the whole spectral facet of graphons, okay, which is an incredibly important direction in graphon theory. And here, much of the theory follows just by thinking of the graphon as a symmetric, non-negative real matrix. Obviously, that's very close to a definition of adjacency matrix. So what we have here is adjacency matrices have eigenvectors and eigenvalues, right? How does it work? Well, that's what linear algebra 1 is about, right? You have the adjacency matrix, you stack a vector next to it, and then sometimes you get lambda times that vector, right? What the eigenvalue and eigenvector are. And you can do the very same thing for graphons, except now you have to rewrite this matrix multiplication, right? When you had a matrix and you would multiply it by a vector. How does it work? Well, you get a vector which at a certain position x is defined by ranging over row x of the matrix and multiplying the individual entries you see there by individual entries of the vector and summing that all up. Okay, and now you do the very same thing, except now your vector is actually a function. So its entries are not indexed by columns, but they are indexed by numbers in the unit interval. And the summation you used to do now becomes integration. Okay, and so once you have the notion of eigenvalue and eigenfunction, then, well, you take the spectrum, which is the set of all eigenvalues. I will return to this in a minute because I'm slightly making a shortcut. And then the spectral radius is the maximal eigenvalue. Okay, so whatever they taught you about eigenvalues or spectral theory of non-negative symmetric matrices has a counterpart here. And let me just recall that the assumption that a matrix is symmetric gives you an extremely strong spectral theory. In particular, all the eigenvalues are real, corresponding eigenfunctions are complete orthonormal set. The same holds for graphons, again, very crucially relying on the fact that the graphon is symmetric. So there exists an at most countable set of real eigenvalues. Actually, the only potential accumulation point of that set is 0. Those eigenvalues are bounded. And corresponding orthonormal eigenfunctions, so that you have this spectral decomposition. The W can be written as lambda I times Fi times Fi. Okay, and now so that's what the spectral theorem tells you. And let me tell you what is conveniently used in graph theory is a version of the spectral theorem for powers. Okay, so power of a kernel, I will have a definition later, but the way you should think of it is the same as power of a matrix. So it's not rising to that power individual entries, but somehow doing some global convolution with that matrix. But if you are looking at the nth power of a graphon at position x and y, then what you have is the same spectral theorem or spectral formula. The only difference is that the individual eigenvalues were raised to that power. Okay, let me give you an illustration, arguably the most important illustration of where this has been used. Cycle density. I will for now assume that people do know what density of a k-cycle into a graphon is. It's some sort of k-fold integral, which is really central in the Lovász-Szegedy theory of graph limits. And this is just the sum of the case powers of the eigenvalues. Okay, many applications. Okay, so now let's move to digraphons. Now, what are digraphons? I haven't mentioned that. And why am I talking about them here? So first, why am I talking about them here? It will turn out that to analyze this inhomogeneous random two-set, digraphons arise. Okay, and so what are digraphons? Well, what is the difference between a graph and a digraph? Well, basically the difference is that in a graph, the adjacency matrix needs to be symmetric, whereas in a digraph, it need not be. Whether there is an edge from x to y has nothing to do with whether there is an edge from y to x. That's the distinguishing property between graphs and digraphs. And likewise, digraphons for me will be just infinity functions defined on the unit square. So I'm dropping this condition of symmetry that wxy equals wyx. That's not there. So I simply call such a function a digraphon. Okay, and now the same way you can do spectral theory for digraphs. Again, you would take the adjacency matrix of the digraph and you would be multiplying that by a vector, the same formula as in the symmetric case. when doing the finite matrices, and the same integral formula when you want to view the digraph as an operator. But now we are in the setting of non-self-adjoint operators. So we are in that part of functional analysis. And that part is more difficult. In particular, there is the notion of eigenvalues. Okay, so the definition, lambda is an eigenvalue if W minus lambda times the identity is non-injective. It happens to be the same. That's just a convenient reformulation of this property we are used to as a defining property of eigenvalues for non-trivial F. And then there is another notion, which is the notion of the spectrum of that operator. And that is that W minus lambda times the identity is not invertible as a bounded operator. Okay? So if something is an eigenvalue, so it's non-injective, so certainly non-injective functions are not invertible. But that's not the only reason for non-invertibility, right? The other reason being non-surjectivity, somehow it happens to be equivalent in finite dimensional vector spaces, but not in infinite dimensional vector spaces. So the definition of spectrum is more general than the definition of eigenvalues. What I want to emphasize at this moment is that the definition of an eigenvalue is in some sense constructive, right? When something is an eigenvalue, you do have this function f to your disposal. The notion of the spectrum is much less constructive. When something is a point of the spectrum, there is no function f you can work with, okay? And so importantly, spectral radius is now defined as the supremum of absolute values over the spectrum, not over the eigenvalues. Okay, so that's actually the proper definition. For self-adjoint operators, actually every point in the spectrum is an eigenvalue, so there is no difference there. But now in the non-self-adjoint setting, everything is much more difficult because these are genuinely different notions. And also, quite importantly, we don't have any spectral decomposition. There is something called singular value decomposition, but no spectral decomposition. To demonstrate a failure of this spectral decomposition, you can consider this very classical operator called the Volterra operator. So it's a digraphon which at point x, y is defined as either 0 or 1, depending on whether x is smaller than y or larger than y. And that's the operator here. This operator has an empty spectrum. It has nothing in the spectrum. So when you look at this left-hand side, you see a very non-trivial function, but actually the summation on the right-hand side, only summation you could think of would be the empty summation. So somehow the spectral decomposition fails badly. Now, this Volterra operator is something to keep in mind. In particular, some things I will be saying on the next slide may actually seem, as being in contradiction to the existence of this operator. Okay, so the main question is there any useful spectral theory for digraphons? And the answer is yes. And while you can say very little useful things for non-self-adjoint operators in general, what helps here is the fact that this operator is non-negative, which more or less is equivalent to your digraphon being pointwise non-negative function. And the corresponding part of functional analysis which deals with such a setting is called the theory of Banach-lattices. Okay? So in particular, there is a powerful theorem by Krein and Troutman, which tells you, well, even though the spectral radius was defined over the spectrum, which is a very different and in general much bigger notion than the set of eigenvalues, actually it is, in case of a non-negative operator, it is equal to the maximum eigenvalue, or equivalently the eigenvalue which is maximum in absolute value. So that's part of the theorem, that the eigenvalue which is maximum in the absolute value is automatically real and non-negative. Okay, and the right way of thinking about the Krein-Troutman theorem is that it is a functional analytic counterpart to the Perron-Frobenius theorem, which is something people who work with, say, finite Markov chains know very well, right? Because a finite Markov chain, what is that? Well, that's just a sort of discrete version of Digraphon. It's not necessarily symmetric, but it's everywhere non-negative. And then the Perron-Frobenius theorem tells you that there is an eigenvector with positive entries, and the corresponding eigenvalue is positive and actually the largest than any other eigenvalue. Okay, you need to assume irreducibility and aperiodicity when you do transition matrices of Markov chains. I guess everything I will say about Digraphons below, I'm sort of sweeping this assumption under the rug. So many of these assumptions do need some sort of irreducibility, or actually, as we call it, strong connectivity and aperiodicity. So actually, there will be some slides about how you decompose a digraphon into strongly connected components later on. I will not talk about periodicity at all. It's swept under the rug, but actually it's quite easy to deal with. Okay, so for example, this Gelfand formula we have here that I think only holds under the assumption of periodicity and irreducibility. So let me try to explain what I call Gelfand's formula. It is in the paper. It took us a lot of work to deduce it. On the other hand, I wouldn't be surprised if this were something standard for people who understand functional analysis well, which we, Petr and I, don't. So for us, it was a lot of work to derive it from general results in functional analysis, but I wouldn't be surprised if this was something well known. And please, if you do know of a reference, then let us know. So I will try to explain this, and I will do that by going back to a slide about graphons. Okay, so remember we had this spectral decomposition like so. And in particular, when you take a large power of the digraphon, well, those lambdas, those eigenvalues, which are smaller than the largest eigenvalue, taking high powers, they become negligible. So under the assumption that there is only one eigenvalue of maximum absolute value, which is a very reasonable assumption and is actually true when your graphon is non-bipartite, when you take a large power, then w to the n at point xy behaves essentially like this principal lambda to the n times f of x times y of x, y at y, where f is the leading eigenfunction. Okay, and this theorem says that you have the same phenomenon here, except you have to be a bit more careful, because now in this non-symmetric setting, things don't have just the principal eigenvalue, but they have the principal left eigenvalue, which is the eigenvalue of the original operator, and they have something called the principal right eigenvalue, which is actually you take the transpose, the adjoint of the operator, and you have some other eigenfunction for the same eigenvalue. Okay, so that's the same as the fact that in finite matrices, say a real matrix and its transpose have the same spectrum, but not necessarily the same set of eigenvectors. And let me say that what we were quite surprised that there was very little known about spectral properties of digraphons. So actually, roughly at the same time as we were putting this on arXiv, Grebikral, Liu, Pikurko, and Slipanchuk posted another paper on the arXiv, which dealt with spectral properties of digraphons. Their results go in different direction. I would say that the most important result of theirs is that they were able to obtain a spectral formula for the density of an oriented K-cycle in a digraphon. Okay, and it's sort of the same formula as in the undirected case. In the symmetric case, what enters the picture is this M of lambda I, that's what's called algebraic multiplicity recall that spectral theory of non-symmetric matrices. Let's say there is the notion of multiplicity is more complicated, and there is what's called algebraic and geometric multiplicity. Okay, so these were the preparations regarding random graphs and spectral properties. Now I want to do a little bit of overview about random K-SAT, and then talk about our model. So a K-set, where the first non-trivial K is 2, 3, and so on, is a Boolean formula in conjunctive normal form, which means that you have some Boolean variables and you have clauses connected with conjunctions, and each of them consists of K literals. Here is an example of a Boolean formula with clauses of length 3. And well, this model is extremely important because of computational complexity. So when Cook introduced this notion of NP completeness and this reduction among NP complete problems, then actually he did use SAT for that. And immediately after, Karp showed that you can do the reduction to 3-set. So deciding whether a given 3-set formula has a solution or not is as difficult as any other NP-complete problem. So that's sort of the community of NP completeness, but now I'm looking at it from a random set. This is something people have been looking at from at least 1980s. And so what's the random model here? Well, you fix K, maybe 2, maybe 3, maybe 4, and you take all K-SAT formulas on K many variables. So you have actually 2n potential literals because every variable comes with its negation. And now you select some of them at random and include them connected by conjunctions into your formula. Okay, so the number of clauses you take is m, and typically m is some constant times n. And what is the most important problem in this era is the so-called satisfiability conjecture. I'm not even attributing it to anyone particular. It has been around and folklore since at least 1990s. And it says that for every k, there exists this threshold function alpha k, so that if you look at random K-SAT on n variables and alpha n many clauses, where alpha is smaller than alpha k, then as n goes to infinity, your random formula is asymptotically almost surely satisfiable. Whereas if you move above the threshold, you are looking at n comma alpha n, where alpha is bigger than alpha k, then your random formula is asymptotically almost surely unsatisfiable. So there exists no assignment of two values of these random variables so that the formula as a whole would evaluate as, well, true or 1. Okay. Now, the case k equals 2 was much, much easier than all the others for reasons that we will see later. And it was solved independently by Hladký and Reed and Gert in 1992. Alpha 2 turns out to be exactly 1. And then people realized that k equals 3, 4, and so on is much more difficult and is connected to statistical physics. And the breakthrough came in 2022 when Ding, Sly, and Sun published proof of the satisfiability conjecture for k larger than an absolute constant. Okay, so what you might argue is that the most interesting case, say k equals 3, that is still open. But this monumental work, which appeared in the Annals of Mathematics, that has more than 300 pages, solves the satisfiability conjecture for all k large. Okay, so now I want basically to show you the solution for k equals 2. Okay, or at least give you a sketch of what Hladký, Reed, and Gert did. They have a very, very similar proof. Okay, again, because I want to generalize or at least take elements of that proof to the inhomogeneous setting. So that's the theorem they proved, and their solution is graph theoretic, or I should say digraph theoretic, and it goes via a connection that had been known even before that, which is called implication digraph. The idea is that if you look at one of the clauses, say at this one, and you know, and you assume that one of the variables is not satisfying, then the valid conclusion is that the other needs to be. So what you construct is a digraph on when you have n variables, then on for every variable you introduce two vertices. One represents that particular variable being set to 0 and the other the variable being set to 1. Okay, and what you do is, for example, let's deal with this first clause, which is read on both in the formula and in the digraph. You know that if x1 were set to 1, then the first term in the formula is not the satisfying one. So in order for the whole formula to be satisfied, and in particular for this clause to be satisfied, x2 needs to be satisfying. So you get this arrow, okay? And similarly, if x2 were not the satisfying variable, then the part negated x1 needs to be satisfying, so that's why you get this arrow. And similarly, if x2 is equal to 0, then x3 needs to be equal to 1. And if x3 is equal to 0, then x2 needs to be equal to 1. So from a formula, you create this digraph. For each clause, you actually introduce two directed edges. And what is the importance of this implication digraph? That's how it is called, of a formula. Well, there is this very simple lemma that the whole formula is satisfiable if and only if its implication digraph contains no what is called contradictory cycle. Okay, so what's a contradictory cycle? Well, that's a directed cycle in the digraph. So a cycle whose edges are all directed in the oriented in the same direction, which for some I goes through these both copies of xi. Okay. Indeed, if you have such a contradictory cycle, then there is no way you could set xi, right? Because you have two options. You could set xi to 0, but then somehow that there is a chain of implications which leads to your need to set xi equal 1. Well, sorry, I started with with the opposite assumption. Or the other option is that you set xi to 1, but that actually triggers a whole chain of implications which tell you, well, you need to set xi to 0. Okay, so this was so far we had a purely deterministic construction. There was nothing where we use some properties of randomness. So does the implication digraph of two set contain a contradictory cycle with high probability or with low probability? So what's the setting? Well, you have your implication digraph has 2n vertices, and hence it has up to something like 2n, that whole thing, square directed edges. Okay, and the number of these random clauses you have in your formula is alpha n. Okay, and we said for each clause you are inserting two directed edges. So into your digraph, random digraph, you are inserting two alpha n directed edges. Okay, so you get essentially a model of random digraphs, which is close to a model of Erdős-Rényi random digraph at a particular density, which is computed here. Okay, it's not exactly Erdős-Rényi random digraph at that density. Why? Well, for example, because the number of edges is always even, right? You always introduce for each clause exactly two edges, but it's very close to that. And what you can easily show is that a random digraph at edge density alpha divided over the number of vertices has very few cycles when alpha is less than 1, and has many cycles when alpha is bigger than 1. Okay, and in particular, when it has few cycles, then you had this additional assumption, which was not graph theoretic, it was Boolean theoretic, about this contradictory property. But among those very few graph theoretic cycles, none of them will be contradictory. Whereas you have plenty of cycles, then at least one of them will be contradictory. So that's sort of the end of the proof. What we did is we talked about random k-set, some historical remarks, but for the case k equals 2, we actually did cover in detail this notion of implication digraph, and in particular this lemma that your formula is satisfiable if and only if it doesn't, the corresponding implication digraph doesn't contain contradictory cycles. So now I want finally to get to our result. Okay, and I need to introduce the model and maybe motivate it. So what was the motivation of generalizing the R-Renyi random graph to this inhomogeneous setting, as Bolobash, Jansson, and Riordan did? Well, because you would argue that the edge probabilities depend on types of vertices, right? Maybe how far two individuals live from each other, that plays a role in determining how likely to form a friendship. Maybe some other more sociology or demographic parameters, like what is their age, might also determine that. So that's what creates this inhomogeneity, right? Likewise, random 2-SAT is model of certain constraints. But again, you might argue that these constraints come from different types, and the probability of a particular constraint being formed depends on the types of variables involved. Now, when I still stay with graphons, then we said that the graphon is a function whose domain is the unit square. Now, the fact that it was a square was not important at all. What was important is that it's a symmetric function on a square of some probability space. And the Lebesgue isomorphism theorem tells you that more or less any space, any probability space under some very mild conditions is isomorphic to the unit interval. Okay, but this will be different in 2-SAT just because every variable has its negated version. So to reflect the fact that every variable comes with its twin or maybe anti-twin, I also need to reflect it in the ground space of the graphon. So every vertex comes with its anti-twin, right? In particular, now I'm working with kernels which are defined on the square of a product space whose first coordinate is plus comma minus, and the second coordinate is whatever probability space. So maybe again the interval 0, 1. This is the picture. You have this interval 0, 1 comes in 2 copies. One copy is with plus, and the other is with minus. Okay. And now, how does so given a graphon, how do we generate a random Boolean formula to set n comma w? So now I'm introducing the model. Well, first you generate representatives of individual variables in this plus copy of the unit interval. That's what I did here. X is equal to 4. Okay. And then automatically, once you have generated that, you have automatically this coupling that it automatically creates these anti-twins, right? Okay, so you have that. And now you start inserting clauses into your random formula. Okay, so on this picture, I'm inserting a clause x1 or x4, which is the same as which is the same as x4 or x1. Sorry. Okay, and how do I do it? Well, exactly as in the Bolobash, Jansson, Riordan point. So I look at the value in the kernel at plus x1 comma x4, and I divide that, I rescale that by, okay, so here somehow that's a matter of convention, by 2n. Okay, so and similarly I could decide for the inclusion probability of the clause negation x1 or x4, which is the same as x4 or negation x1, but it's something different than x1 or negation x4, right? So I have different points to look for that. And okay, what I haven't done is that also I may decide to include or not to include the clause negation x1 or negation x4, right? So that, where would I look for that? Here, right? This would be the probability of insertion of negation x1 or negation x4. Okay, so there is a slight difference compared to the homogeneous case, that in the homogeneous case we said, oh, and let's take, you know, deterministic number of clauses, which was alpha n. Now I'm saying, oh, I flip a coin for every clause to include or not to include. Hence, in theory, my random formula, the number of vertices is not fixed, and in theory could be anything between 0 and everything. But of course, it's concentrated around some constant times n, and that constant happens to be the L1 norm of W. And in particular, when W is the constant alpha, then you recover this 2-sat where you are including alpha and many clauses, so the homogeneous case. Okay, so again, that was the setting. This is the model we introduced, and the point of it is that it's good for modeling these inhomogeneities. And the main theorem is, well, take any kernel you want, do something with it, I will explain what that something is, and compute the spectral radius of that something. Okay, so that something here, I call it maximum over all strong components that are contradictory of the spectral radius of the implication digraphon corresponding to W. Okay, so we will get to it, but you have some sort of spectral radius parameter, and then if that number is smaller than 1, then your inhomogeneous random 2-sat is asymptotically almost surely satisfiable, and if the spectral radius is bigger than 1, then it's unsatisfiable. Now, this complicated rho star parameter, of course, when W is constant alpha, then rho is equal to alpha. So in particular, we do recover the Hvatal-Reed-Geertz theorem, because in those cases, you know, computation of the spectral parameter is very simple. Okay, so that's the theorem. It does determine asymptotic almost surely satisfiability and unsatisfiability. And by the way, let me note that this parameter rho star is multiplicative. So what you could do is you would take a kernel whose rho star would be 0.7, whatever, and you would multiply it a little bit, and the spectral radius would stay below 0. And once you are sort of multiplying it by bigger and bigger numbers, where it's exactly 1, and from that point on, it would be more than 1. So the inhomogeneous model exhibit a phase transition of satisfiability as well. Okay, so now I will have several slides in trying to explain what operation you need to do to get the spectral radius. And the first is that you don't work with W, which again was a symmetric function. You wanted that. If you want to parameterize inhomogeneous random 2-sat, you do parameterize it with a symmetric function, but very quickly this leads to a non-symmetric version, which I would call implication digraphon, which is some sort of a transposition which very much mimics the transposition which happens from when you are transforming a Boolean formula, which is sort of a symmetric thing, right? So if you have a clause x1 or X4, then you are thinking as the transposed clause X4 or X1 there being there as well, right? There is this symmetry there. But what it very quickly leads to is this asymmetric implication digraphon. Okay, so this is how this implication digraphon works schematically. The underlying graphon W of the two-set model has three parts. A, which encodes what is within the plus part, what is happening for clauses which have two positive literals. Then there is this part B, which is describing what happens for clauses with one literal positive and one literal negative. And then there is this symmetric part, C, which is describing what's happening for two literals with negated variables. Okay, and you mechanically take these three parts. One of them, the B part, appears there twice. One is sort of a mirror image of the other, and you move them into the digraphon. So that's what the implication digraphon corresponding to W is, and you see that we lost symmetricity. Okay, to illustrate this concept of contradictory components, I want to consider a specific digraphon or graphon, and that's the graphon on the left-hand side. So three parts of it are constant 999, and only the part which is describing the densities of clauses with two negated variables of various types is constant 0. So such clauses will not be included. Okay, so formally we will have plenty of clauses with two positive variables. Why? Because the value here is huge. And they have plenty of clauses with one variable negated and the other positive. Okay, so we get our random formula is very long, but at the same time it is satisfiable because we can set everything to 1. Okay, and now if you want, you can see it from the implication digraph and digraphon. So the implication digraphon will not, so remember, it has the vertices are of two types, representing versions of the variables when set to 0 and versions of the variables when set to 1. And there is not a single arrow from the 1 part into the 0 part. Okay? So what we have is this implication digraphon, which has actually a huge spectral radius in itself. You can calculate that its spectral radius is, well, 499.5. That's what turns out to be the correct value. Yet, somehow, this rho star, which we haven't defined yet, needs this to have spectral radius less than 1, because what we see is that we are in the asymptotically almost surely satisfiable regime. Well, and when we are working with such huge numbers and still the spectral radius, this rho star is required to be less than 1, then I guess there is no other option than having it 0. Okay, so we need to find a concept in which, or understand why this rho star of such a digraphon should be 0. And to that end, we need to understand what components in digraphons are. So surprisingly to us, this is a concept which hasn't been worked out for digraphons. For graphons, there is a decomposition into components, which is a counterpart to decomposition into components of finite graphs. That was done by Jansson. And what you say is that a set in the unit interval is disconnected for a given graphon if there exists a subset of it Y, which is proper, meaning it's not a null set and it's of strictly smaller measure, so that y and the rest of the x don't communicate. So on this cross section y cross x minus y, w is constant 0. Okay, and the decomposition result is that just like every graph admits a decomposition into connected components, and the decomposition is unique up to order, every graphon admits a unique decomposition into components. So I haven't defined what components are. These are things which are not disconnected, sets which are not disconnected, and they are in some sense maximal. Okay, and further, there is what's called a zero set. So that would be a set of vertices where the corresponding slide is constant 0. Okay, so now what we did is we obtained similar results for Digraphons, but I first want to recall the situation with finite digraphs, because their things are more complicated than in finite graphs. In particular, there is not one notion of connectivity, but two, and I want to talk about the stronger of them, which is called strong connectivity and corresponding concept of strong components. Okay, so as an example, let's consider the finite digraph I have on this picture. So it's a digraph on something like 15 vertices. And what you see in the digraph is that it has the vertices can be partitioned into two parts, which are quite big. Okay, and what's happening within each of these parts is that there are arrows going in all possible directions. Okay, maybe not all arrows, but there are many of them, and they are going in all possible directions. And then there is this intermediate part, and what you see is that those edges, in those directed edges in this digraphon, which are not confined either to the box on the left or to the box on the right, they only go from left to right. Okay, so in particular, strong component is a maximal set of vertices such that between any two vertices within that component there exists an oriented path in both directions. Okay, and what these boxes is a decomposition of this digraph into connected components. Now, you could consider some sort of limit version of this, okay, where what would be, so producing larger and larger digraphs somehow following this pattern, in particular in a way that the middle third of the vertices are each of them forms a trivial connected component. Okay, if you look at the corresponding limit digraphon, you would end up with a picture like so. Okay, and that digraphon actually has a decomposition into strong components, which are x1, x2, and then there is this zero set x0, okay, which emerges as a limit of smaller and smaller connected components. Okay, so here are all the notions. We have this notion of a strongly connected set, a corresponding notion of maximal components, and there is a decomposition result that every digraphon admits a unique decomposition into strong components. So now let's look at it. What's happening here? Well, if I apply this notion to the implication digraphon we just created, we see that that digraphon itself is not strongly connected. It has these two strong components, which I depicted on this picture with green and red. And it, like, one way to see that it is not really one strong component is that if it were one, you need to find arrows, at least one arrow from the red component into the green. Obviously, there is no such thing. Okay, so on the implication digraphon, we will always apply a decomposition into strong components. Why is it meaningful? Well, remember we are in search for contradictory cycles. And if you want to search for contradictory cycles in a digraph, then it's enough to do it strong component by strong component. Each contradictory cycle needs, because it's a directed cycle, it needs to be confined to one component. Okay, so let's give now more details to our theorem. So we start with a graphon which underlies our inhomogeneous two-sat model. We consider its implication digraphon D, and we decompose that digraphon into strong components and a zero set. Okay, and now we discard some components. And which components do we discard? We discard those components which have no chance of hosting a contradictory cycle. So remember, a cycle is contradictory if it goes through a vertex xi equals 0 and xi equals 1 at the same time. Every such a cycle, its vertices need to be confined to something I would call a contradictory component, which is a component which contains vertices of the form plus x and minus x for the same x. Okay, so it touches both the positive side of our ground space and the negative side, but that's not enough. It also touches them at least partially at the same place. Okay. In particular, on this 999 example, there is not a single contradictory component because we have two components and one of them is confined to the plus part and the other is confined to the minus part. Okay, so we mark those contradictory components. They are the only potential source of contradictory cycles. And then, okay, so we look at the digraphons induced by these contradictory components. For each of them, we compute the spectral radius and we take the maximum of those. Okay, and that's this parameter rho star of W. So now I believe I explained all the definitions for the main theorem to make sense. Okay, so the statement of the main theorem should be clear now. And what I want to do is I want to give you a hint of the proof. And so what is the setting? The setting is that we are looking at a digraphon and we are generating a random graph from it. And we want to see whether there are cycles, contradictory cycles perhaps. Now, if I have a vertex in such a random graph whose type is x and another vertex whose type is y, and I want to know what is the density of paths, of directed paths of lengths, say k, between x and y, then that's exactly what this power of the operator d expresses, right? And okay, so now I have written down the full formula. And now I'm using that this number grows as roughly rho, the spectral radius of to the power of k. Okay, so that's what we will be using. So how shall we use it? Well, we fix a potential contradictory cycle. Okay, so what is that? Well, there is a special vertex y, which is present both in its positive form and in its negative form. Okay, and then so from y to the y negation, there are k many sort of dummy variables on the cycle, and from y negated again to y, there are further h many. Okay, and so when you are creating this random digraph, which emulates the clauses being presented, then the probability that this fixed choice of your vertices is a contradictory cycle is precisely expressed by this integral. Okay, And now using our Gelfand's formula, what you have is that this is theta of the spectral radius of the digraphon to the k plus h times n to the minus k plus h plus 2. So the exponents are almost the same. They are off by 2. Okay. Now this was for a fixed choice of your variables y, x1, and so on. But actually, we will be fine with any contradictory cycle. So we are doing a union bound, and the number of choices is something like n to the k plus h plus 1. Okay. So what you get in the unsatisfiable regime, so if your digraphon has spectral radius strictly more than 1, then by taking k plus k and h to be logarithmic, you get that the expected number of cycles, contradictory cycles, goes to infinity. Okay, so in this case, you do get, in expectation, infinitely many contradictory cycle. You need to do some sort of second moment argument to get that. Asymptotically, almost surely there is at least one. Of course, in the satisfiable regime, when rho is smaller than 1, things are even easier. And what you get is that the expected number of contradictory cycle goes to 0, and hence there is none by Markov inequality. So that concludes the proof of the theorem.